need to analyze the problem. There are two processes here. One is collision. Then the another is after collision, they will swing up. So during the collision, here, plot it with the speed, initial speed, the velocity v, with the mass m. The block is uppercase M. Then after collision, so the body will just stay inside that block. Then the two objects merge into one object. They acquire the final speeds, Vf. So during this process, collision process, along the horizontal direction, there is no external force. Along the horizontal direction, there is no external force. So when the bullet is interacting with the block, there is a friction between the block and the bullet. Those frictions belong to the so-called internal force. Okay, internal force for the system. The system consists of the bullet and the block. So, but there is no external force. You didn't apply the external force on that system along the horizontal direction. So, under that condition, the momentum conserved. The linear momentum conserved. Okay? So, we just analyze the initial momentum before the collision, just the momentum of the bullet. Because initially the block pendulum is just steel, so there is no velocity. The velocity of the block is just zero. So initial momentum is just the momentum of the bullet, just the m times v. The final momentum, just after the collision, the whole thing still didn't get a chance to swing up. Just before begin to swing up. Just at that point, the two objects, the bullet and the block, acquire the same final speed. So that final momentum should be the total mass, m plus the uppercase m, times the final speed. Okay? So just says the two momentum equals the initial momentum equals the final momentum. Then you get mv equals m plus the uppercase m vf. Then you can solve the final speeds of the two objects. Just the mv divided by m plus uppercase m. Okay? Then the second part, the second process, the two objects together swing up to this position. The maximum height from lowest point to the maximum height is h. For this process, there are two forces here: gravity and the tension in that cord, and the gravity. The tension is not conservative force, but the length of that cord doesn't change during that process when in the spring. So the length of the tension, the length of the cord doesn't change. So that force in that cord, the tension in that cord, doesn't have any displacement. Okay? Because that length of that cord doesn't change during the swing up. So that force in the cord didn't do any work because it had no displacement around that direction. Okay? So that only force left is just gravity. Gravity is a conservative force. So we said in that system, you only have conservative force do their work for that system, the total mechanical energy is conserved. So during that string up process, we use the conservation of mechanical energy. Okay? Conservation of mechanical energy. So we just analyze the two positions, the lowest position and the highest position. The lowest position, the total energy, just the kinetic energy plus the potential energy. Kinetic energy at that time, the two objects occupy the same final speeds. So kinetic energy just the half the mass of the two objects times the final speed squared. Plus potential energy. Potential energy, we can choose the lowest point to the y-coordinate is just 0. So in that way, so then potential energy is just the times 0, m plus m times g times 0. Then the final point right here, highest point h here. The highest point, the speeds of that two objects just 0, because we get the highest points. So that speed at that point is 0. So kinetic energy just 0. Then plus potential energy coordinates is just compared to 0, just the s. So potential energy just the n plus this n times g times h. So we can from here relate the final speeds and the h. Cancel this. Cancel the m plus n. So the final speeds also relates to the h, just the 2gh. Okay? Final speed squared equals 2gh. Then the final speeds relates to during the first collision process is given by this. So we set them, put that one into that equation. So we get this one can take a square root. So that way we can get mv divided by m plus n equals square root 2gh. Then we relate the initial speed of that bullet with this height. Okay? Just the m plus n g by sn to gh. Okay? So that's the results they're asking you. Relates the initial speed of that bullet to of the maximum height. Okay, any question about this? Just two processes. One is collision, so we use the conservation of linear momentum. The second process is just the string up. It only conservative force do the work, non-conservative force tension didn't do any work, so that mechanical energy conserved, so we can release the height and speed. Okay, so let's look at the next one. The next one is 38. So we didn't talk about the 38 in the previous revision, right? Didn't. So okay, that's it. 38 talking about you drop a 14-gram ball from a height of 1.5 meters and it only bounced back to a height of 0.85 meters. What about the total impulse on that ball when it hit the floor? Ignore the air resistance. Okay, the impulse. Let me draw the picture here. So the floor is right here. So the ball is dropped from this height, initial height h1 equals 1.5 meters. The mass is 14 grams. So when the ball hit the ground will be exert force on that ball up. When the ball hit the ground will exert force on that ball up. Then the ball will bouncing up. apply the speed V2 here. Before the ball is hit the ground, the speed is V1 down there. Then the ball will go to the height h2, it's just 0.85 meters. Okay, the impulse due to the force. Because the floor exerts a force on that ball, the floor will exert the impulse on that ball. The impulse on one object is just the change of the momentum of the object. Okay? The impulse on an object, just the change of the linear momentum of that object, or equals the momentum of final points minus momentum of initial points. Okay? We're talking about that same object. Here, that's the ball. That's the impulse on that ball from that floor equals the change of the momentum of that ball. So, in order to calculate that impulse, we just calculate the momentum before and after the collision. Before the collision, the ball is moving downwards with the speed v1. That v1 relates to that height h1. Because during the process, the free fall, we ignore the air resistance. So the only forces during the free fall, is just the gravity. Gravity is conservative force. So during that process, we can use the conservation of the mechanical energy. So we can determine that V1. So we use then mechanical energy, conservation of mechanical energy. At this point, you drop it, so initial velocity is just 0. So it's going to be just the potential energy mgh1 equals final point right here, only have kinetic energy, just half mv1 squared. Okay? So the v1 we calculate is just 2gh square root. Similarly, for the v2, we're just talking about the bouncing up process because the air resistance is ignored. So this is the conservation of mechanical energy during the bouncing up process. The initial point right here only have kinetic energy, just the half mv2 squared equals final point right here only have mechanical energy, potential energy, just the mgh2. So V2 equals 2gh2 square root. Okay, so you got the two speeds, you can calculate the momentum. But remember, the velocity before collision is going down. The velocity after collision is going up. So we choose the up direction is positive because that direction follows the direction of the force. So let's follow the direction of that impulse. So that change in momentum should be the final momentum, and it's the mv2. mv2 is positive minus initial velocity, initial momentum, mv1, but initial momentum is going down, is negative itself. But this negative side is coming from the difference. So here you need to use another negative sign to denote the direction of the initial momentum. Okay? This negative sign just to tell you the direction of the initial momentum. Final momentum is positive. Initial momentum is negative. This minus sign just tell you the difference, the change in momentum. Okay? Okay, you find just the mv2 plus v1 actually. This one means just the magnitude and together. Magnitude we calculate here. So that means we just m square root 2gh2 plus square root 2gh1. Okay? Just like this. So, okay, so right now we can put in the number. So convert to the standard SI units. So then the mass is 0.014 kilograms. Square root 2 times 9.8 times H2, then it's 0.85 plus square root 2 times 1.8. H1 is 1.5. Those same with the units, just the speed, momentum, just speed, meters per second. Okay, so finally we get 0.13 kilogram and meters per second. Okay, so that's the moment impulse. That's also units of momentum. Direction upwards. Impulse is a vector. It has a direction. This direction is just the direction of the force. Okay? Because that force is upwards, the impulse is also upwards. Okay? So any questions? Just remember, the key is you need to calculate the change of the momentum. But sometimes the momentum with different sign, different direction. So that change should be the subtraction between the two vectors. Subtraction between the two vectors. Okay. This vector is going up, and that vector going down. The subtraction actually is just the magnitude, just the summation of the magnitude of the two vectors. Okay, so that's the problem in chapter 7. So let's look at the problem in chapter 8. So the first one is problem 5. Problem 5 talking about a platter of hot drive rotates at 200 RPM. So when you look at, when you see the RPM, that's actually tell you the angular velocity. Just in the revolution per minute. Revolution per minute. So that's angular acceleration, okay? So the first question, what is the angular velocity in radians per second of that platter? Okay, just convert to the units. You have the angular velocity or angular speeds in 7,200 RPM, means revolution per minute. So you need to convert to radians per second. One revolution means one term of circular motion. One revolution is just one term of circular motion. So that is just 2 pi in radians. So that means you need times the 2 pi radians per one revolution. Then you need to convert the minutes to seconds. That's easy, just divide by 60. Okay, so then you will get how many radians per seconds. Just do that number times 2 pi divided by 60. So we find 753,198 radians per second. Okay? So the first one. Second one, asking you, if the rib head is located 3 centimeters from the rotation axis. What is the linear speed of the point just under the on the platter, just under the reader? The platter is rotated on the central axis. The reader is here. There is the reader. The read head is right here. The distance to that center is 3 centimeters. So that platter is rotating. The point is just under that reader right here. So that is the relation between the linear speed and the angular speed. Linear speed is just equals the angular speed times the radius of that point to the rotating center. Okay? In this case, they are just equal 3 centimeters. So we can calculate the linear speed there at that point. It's just use that angular speeds in radians per second, so 753.98 times the radius, just 3 centimeter, 3 times 10 to the minus 2 meters. Okay, so we find the linear speed is 22.62 meters per second. Okay, the next point asking you if the single bit requires 0.5 micrometer of length along the direction of motion, how many bits per second can the reader and the writing head write when it is 3 centimeters from the axis? Still then to reader is just the same size. So linearly, the bits is just linearly located on that circumference. One bit you need 0.5 micrometers. Then they ask you how many bits per second recovered by that reader. In 1 second, the reader will cover the distance just 22.6 meters. One bit just 0.5 micrometers. So you just use that number divided by the length of 1 bit. So that's the number covered, or bits covered in 1 second. Just use that number divided by the length of 1 bit, 0.5 micrometers. This is the meter per second. Okay? So then you get the how many bits in 1 second. Okay, so then you get 4.5 times 10 to the 7 bits per second. Okay? So this problem is just to review that concept about the angular speeds and the relation with the linear speeds. The second problem, 14, talking about a 61 centimeter diameter wheel accelerates uniformly. Uniformly means the acceleration is the constant about its center from 120 RPM. So when you say RPM, that tells you the acceleration, angular velocity, angular speed. From this angular velocity to 280 RPM to another angular speed in 4 seconds, determine the angular acceleration. Okay, so just like the formula in 1D motion, instead of just x coordinates there, we're talking about just angle. Okay. Okay? So that relation, acceleration, angular acceleration, just the changing rate of angular velocity. Just the changing rate of angular velocity. Here they tell you the final angular velocity and the initial angular velocity. So just the changing rate, final velocity, angular velocity minus initial angular velocity divided by the time of the interval. Okay? So in this case, what they tell you in RPM, you need to convert to radians per second. Okay? So the final angular speed is 280 RPM. Convert to radians per second, you need to times 2 pi divided by 60. Initial angular velocity 120 times 2 pi divided by 60. That in number units are radians per second. Then divide by 4 seconds. Let's say just 4 seconds. Okay, so then you get the angular acceleration. You calculate, you will find the number is 4.188 radians per second squared angular acceleration. The second part, the radial and the tangential components of the acceleration of the point on the edge of the wheel 2 seconds after it has started accelerating. So in order to calculate the radial and tangential acceleration, radial acceleration, we talked about that before, about circular motion. We use later AR is radial. Acceleration tangential, I use AT. For circular motion, we have the universal formula for the centrifugal